Okay, hey guys, hope everyone's doing all right. Welcome to hopefully week 2. This is lesson 3 in financial modeling. Today we are doing geometric sequences. So we've already looked at arithmetic sequences, which is where we're adding a common difference each time, okay, to each term. Today we're looking at geometric, where I won't spoil it, but instead of adding, we're going to be doing something different. So we'll jump right into it. Again, if you have any questions, please just post on the teams, email me, get in touch. All right. So having a look at this first example, you can tell that it's not arithmetic by just simply checking, well, what did I add to that first term to get from 4 to 8? I must have added 4. Now, if it's a arithmetic sequence, we're adding the same amount each time. That would mean that I'm adding 4 to get from 8 to 16. That doesn't work out, so it mustn't be arithmetic. So instead, what we're actually doing here, and hopefully you can realize this, is we're actually multiplying. Okay, and that's what makes a geometric sequence geometric instead of arithmetic. Instead of adding a constant, we are in fact multiplying a constant. And we are multiplying by that constant each time. You might have recognized these as the powers of 2, where we're adding multiplying an extra 2 each time. So that's the definition of geometric series, or sequences, sorry. Rather than adding a constant, we are multiplying each term. I'm sorry, am I getting you seasick? Multiplying each term by a constant. So we refer to that constant factor as the common, same as common difference. We're going to start with common, but this time it's a ratio, okay? Because the numbers are being multiplied by the same thing each time, we're calling that a common ratio. It's basically scaling up each number. So thus, for this sequence, we know that because it multiplies, it must be geometric instead of arithmetic. Now, A is going to be the same thing as it was when we did our arithmetic sequences, where A is our first term. So A here is just 4. Now, a common ratio, we already noticed that we are multiplying by 2 each time. And in a second, I'm going to give you a formula that you can use so that you have a bit of structure and it's a bit more formulaic instead of trying to figure it out yourself. But for this one, it's quite easy. We are multiplying by 2, so that is our common ratio. Wicked, not too bad, hey? If you wanted a more formulaic approach to find that common ratio, we can use this kind of formula here, but it's really more an idea where the ratio is going to be some term divided by the term before it. Because if you took some term, so 8 for example, and you divided it by the term before it, 4, what you're going to be left with is whatever ratio or whatever number you had to multiply to end up with that term. So if we do this, we get the answer 2, and you could do that for any sequential, we'll go with that word, terms. So if we grab 32 over 16, same deal, you're still going to get 2. Okay, so that's the formula for finding the common ratio. Really, we're just saying grab a term, divide it by the term before it. So let's do that with an example. Here, A is always just our first term. So it should be really obvious unless it's in an example where we're going to have to find A, which would be really mean. So here, A is just 100. Now, R, our common ratio, let's use a formula so that we have a pretty consistent approach. So we're going to grab our second term, negative 50, and we're going to divide that by the first term, so 100. Now, if I simplify that, I'm left with negative 1/2. Now, a negative ratio, and it's a fraction, by the way, so you're noticing 2 things. The first thing, because it's negative, each time I divide by negative, I'm going from positive, negative, positive, negative, positive, negative. Okay, because it's going to have double negatives and it's going to cancel out. The other thing to notice is that it's actually decreasing in size each time because you are multiplying by a fraction. In other words, you're dividing, okay? But we still call it the common ratio. We just always do it as multiplying, so it's just multiplying by a fraction. Okay, cool. So recurrence relations we did with arithmetic sequences, where we said if you want to write a term in terms of the term before it, its previous term, you can just do that, and then you're going to be adding on the difference. And that made sense because we said, like, all right, well, if you want like the third term, okay, well, it's whatever the second term was, adding on that common difference. So we can do that with geometric sequences as well by saying a term is going to be the term before it. But what do you have to do to like move along the sequence? It's not adding, it's multiplying by that ratio. And that works. If you like reading it like that, you're golden. It tends to be written with the ratio out the front and then just writing the previous term, because we know that in algebra we tend not to write times, so we can write it as that. Regardless of which way you write it, what we do need to include to be consistent with what we did last week when we wrote the arithmetic sequence recurrence relation is at the end we need to write, okay, so that's all good, but also the first term was A. We always do it at the end. So if you're doing a recurrence relation, if you ever asked to find the recurrence relation, my hunch would be they would probably give you some kind of scaffolding to fill in. But in this case, we're going to be writing the ratio times the previous term, comma, and the first term was this, right? Getting in the last word. So let's do an example to kind of like draw a pattern and get a formula out of this. Excuse me. So having a look at this sequence here, the A term is going to be our first term. So straight away, that's just 5. Easy. Now a ratio, we'll use the formula again, just so we're a bit consistent. I'm going to grab the second term divided by the first term, and I get an answer of 2. It makes sense that it's 2 because we're doubling each time, and the numbers are getting bigger and bigger as we go. So I know that A is 5, R is 2. So come to this table, the similar one that we did for arithmetic sequences, and we're going to write for n being the spot or the number of the term, Tn being the answer, so what is the term at that spot, and we're going to write a pattern in terms of our A and our R. So for our first spot, it's always just A, right? So we're going to write our A, and we're going to have 0 lots of the ratio because we don't have the ratio yet, it's just A. Now for the spot after that, remember what we do is we're going to be multiplying by that ratio. So basically 1 of the ratio. Now our third spot, we got an answer of 20, and we can write that as our A value, but this time we've got another 1. So we've got another times 2. So you could write it like this if you so choose, but we can write that as 2 squared. And you can see that next one would be 5, and we're going to add on another to that power. So now it's 2 cubed because we're just multiplying by another ratio each time. So if I wanted to write this at the end for this example, I would say, well, for any spot, I'm going to be writing my A value times the ratio. But you'll notice with these powers and the spot that they're in, we've always got 1 less as my power than I do for the spot that it's in, because we start in spot 1 with the power of 0. So it's always going to be our A value times our R value, where the power is 1 less than the spot that we're in. So if we were to write this as a general formula, what we would do is we'd say, well, it's going to be our A value, whatever that is, multiplied by our R value, so AR, but we've got 1 less R than the spot we're in. And that formula just there, I'll highlight it in blue, so it's super obvious on what we're talking about just here, is the exact same formula on your reference sheet. So you can see it goes arithmetic sequence, arithmetic series or sums, geometric sequence, so you can probably guess what that's going to be. Okay, so let's do a couple examples so that we can put that formula to use. So for the sequence 810, 270, blah, 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 we want to find an explicit rule And that's what we call this. This is our explicit rule. For the nth term, so we're going to write it in this form, and hence, so using our formula, we're going to find the 8th term. Okay, so let's start with what we know. We know A. A is always our first value, and for this sequence, that's clearly just going to be 810. Okay, now we also know how to find R, our common ratio. We're going to grab any term. I'm going to start with 270, and we're going to divide by the term just before it, so 810. Now, if you pop that into your calculator, you should get 1/3, 1/3. And that's our ratio. It makes sense that it's a fraction because our terms are decreasing in size. Okay, now we know how to write our formula because we looked at it just here. Ignore that little dash above it, and it's also on your reference sheet. Okay, so it's always going to be, for any spot, that's why I'm considering n as the number of the spot, it's going to be our A value multiplied by our, and we might do this bit in brackets, okay, just for a bit of nicety. We're going to do our R value, so it's multiplied by our R value, but that R value, and it's especially important to have those brackets when you're doing a fraction, because if you just do a power on the top number, it's very different to doing it around the whole fraction. And it's going to be 1 less than the spot we're up to, so n minus 1. And that's our explicit rule. Can't really be simplified because I don't know what n is yet. But the second part of the question was to find the 8th term, so that's going to be the 8th spot. So if I pop n in as 8, I'm going to get 810 times 1/3. Now, 8 minus 1 is just 7, and you can just write it that way. You don't have to do the full work and do an extra spot just to go 8 minus 1 is 7. Okay, and if you pop that, just this bit right here, into your calculator as is, you will get an answer of 10/27. Okay, and that's it. That is the 8th term. The same thing as if you were to continue that sequence on, where that's first, second, third, fourth, for another 4 terms. Okay, so if we have a geometric series, now in this case, really, this should be a geometric sequence, but we're going to ignore that for a second there. If it has term 3 being 12, so in the 3rd spot, we get an answer of 12, and in the 6th spot, we get an answer of 96. What they'd like us to do is to find the recurrence relation for the sequence. Now, we don't have an A, and we don't have an R. So what we're going to have to do, we did a really similar example with arithmetic sequences, is we're going to have to set up some equations with what we do know, and we're going to have to kind of manipulate that algebra to find A and R, and then pop it into our recurrence relation. Okay, so let's start with what's our usual formula. Our usual formula on our reference sheet is that for any term, it's the A value times the R value, where we have n minus 1 as the power of r's. Okay, so now if T3 is 12, that means that I'm going to have an answer of AR squared, because 3 minus 1 is 2. And now that T3, I'm actually going to replace that with what T3 is, which is 12. Now I can do the same thing with T6. I'm going to get 96 when, now remember this was T6, I've jumped straight to the answer this time. I'm going to have 1 less as my power, so 5. Now I've got 2 formulas here. This is called simultaneous equations, where we've got 2 variables to find, 2 pronumerals, okay? And we've got 2 equations. The way that I like to do these, and I'll swap to a different color so that this method kind of stands out, because there are, again, different approaches that you can use.